Hey there! In this video, we're going to take another look at quadratic expressions and a pretty clever technique that is called completing the square. Well, where this technique comes from is a pattern that we can notice that is the result of squaring a binomial. So binomial meaning two terms, and we're going to square these two terms. First, I want to note that the expression we have written down right now is not the same as x squared minus 4 squared. When we are squaring a polynomial, we need to multiply this entire polynomial times itself. So the meaning of this expression is really x minus 4 times x minus 4. And if we multiply that all out, x times x gives us x squared. Negative 4 times x is negative 4x. And negative 4 times x, again, negative 4x. And finally, negative 4 times negative 4 gives us 16. We can combine these two like terms in the middle, so our final answer is a trinomial, a three-term polynomial, x squared minus 8x plus 16. Now let's take a look at the coefficients in our trinomial and see if we can make sense of them as they relate to the original binomial that we started with this x minus 4. The coefficient of our linear term, the x term, this negative 8, what that came from was the two copies of negative 4 that we added together in this step. So if we call this negative 8 the coefficient b, then another way that we could write this negative 4 is that this coefficient is half of b, or b over 2. Looking at this 16, where that came from was two copies of negative 4 that were multiplied together. So another way that we could think about this term that we're calling c is that it's this negative 4 times itself. And if we're calling this negative 4 b over 2, well, another way that we could write c is that it's b over 2 times itself, or b over 2 squared. Let's multiply out another example and see if that same pattern holds up. So let's see if this works with the binomial x plus 5 squared. So x plus 5 squared means x plus 5 times itself. X times x gives us x squared. 5 times x gives us 5x. We have another set of 5x, and 5 times 5 gives us 25. So in our trinomial that we get from squaring that binomial, we have the coefficient b equal to 10. Now the original constant term in our binomial was 5. And that is indeed half of 10, or b over 2. The constant term in the trinomial that we have at the end, c, is equal to 5 squared. And if b over 2 is 5, 5 squared equaling c means that we could also write this 25 as b over 2 squared. So we can see that this pattern holds up in both of these examples. And indeed, since squaring a binomial will be the same method no matter what number we have in our original binomial, this pattern is true for any binomial squared. Polynomials that have this pattern are called perfect square trinomials because they're the result of taking a binomial and squaring it. So this leads to a technique that's called completing the square, which is trying to take part of a polynomial, a set of terms, and figuring out what constant term we could add to these two terms that we have already to turn this into a perfect square polynomial. Well, in order to do this, we're going to use the pattern that we saw on the previous slide. If we call this coefficient b is equal to 20, then the binomial that would result in this trinomial is the one that has a numerical term that is half of b from our trinomial. So if b is equal to 20, then we can use that to figure out that b over 2 is equal to 10. Then to complete the square and get our perfect square trinomial, we need to add the constant term that is b over 2 squared. So since b over 2 is equal to 10, b over 2 squared would equal 10 squared, which is 100. So the missing term that we could add to this polynomial and complete the square is 100. And we could then rewrite that trinomial as x plus 10 squared. So that technique is called completing the square, and on the next slide, we'll see how that can be used when we're trying to factor polynomials. But let's do another example here, figuring out what constant term we would need to add to this polynomial in order to complete the square. So it all comes down to the coefficient in the middle here. If b is equal to negative 11, what we want to find is then half of b. So half of b would be half of negative 11, or negative 11 over 2. In this case, since 11 is an odd number, when we divide it by 2, we're going to end up with a fraction, but that's okay. We can still square that fraction in order to get the constant term that we would need to add to complete the square here. b over 2 squared would be negative 11 over 2 squared. And when we're squaring a simple rational expression like this, just a numerical fraction, we want to square the numerator and square the denominator. Negative 11 squared is 121, and 2 squared is 4. Notice that since a negative times a negative is equal to a positive, the constant term, the term that's just a number when we're completing the square, will always be a positive. Let's do one more example completing the square, and then we'll see how this trick can be applied so that we can factor polynomials that we wouldn't have been able to factor using some of our other techniques. So the linear term here has a coefficient of negative 6. So if we're going to write this as a perfect square, then we want to take half of b, and half of negative 6 is negative 3. Then to figure out what term we could add to complete this square, well, we want to take b over 2 and square it, so that would be negative 3 squared, which gives us positive 9. So starting with the terms x squared minus 6x, if we then add on the term plus 9, that completes the square and allows us to write this polynomial as x minus 3 squared. Completing the square is a pretty clever trick because it's going to allow us to break apart polynomials that previously we wouldn't have been able to do using some of our other factoring methods. For example, let's take this trinomial x squared minus 6x plus 11. Can we factor this? Well, using our traditional ABC method, looking at the coefficients here, we would try to find two factors that multiply together to equal 11 and add together to equal 6. And no matter how hard we try, there are no factors of 11 that we can add to get negative 6. But we can notice that the first two terms here are something that we can complete the square on. So we see up here that x squared minus 6x plus 9 does simplify into this neater binomial that is squared. So what if we separate this plus 11 into two different constant terms, and we rewrite this polynomial as x squared minus 6x plus 9, because we know that that 9 is something that would complete the square for these first two terms. And then we also have this plus 2, since 11 is a combination of 9 and 2. So even though we could not use ABC factoring to break this polynomial apart, we can rewrite part of it as a perfect square, which we can then rewrite as a binomial. So another way to write x squared minus 6x plus 11 is as x minus 3 all squared plus 2. Now this isn't quite as simple as something that we could get using ABC factoring to rewrite this as just a pair of two factors, but it's pretty darn close because it's just a pair of factors multiplied together plus one additional constant term. And ABC factoring is not something that will work on every trinomial, but completing the square is.